Hey everyone, it's Stoltz again from Stoltz-World, here to bring back some math to the classroom and to hopefully fund my retirement. Um, and I don't know how to get rid of that. So here we go. What we have going on here is we have a situation where we've got a mathematical induction proof. So we've got to prove that 1 minus a to the n is greater than 1 minus n times a for n when n is greater than 2 or equal to 2, and a is between 0 and 1. Okay, so what we're going to start with is let us start with our base case, right? So we have to do the base case, always an important step. So in this case, n is equal to 2. And the reason why it's equal to 2 is because that's what it tells us there. So if I did that, I would add 1 minus a to the n is greater than 1 minus na. Oh, and I have to make sure that I point out that a is between 0 and 1. Why that's important is this right here. If a is between 0 and 1, then this will always be positive. So it'll never be 0 because it's strictly between 0 and 1. So it can't be 1, but it can be 0.99999. And it's strictly larger than 0, so I can never be 0. So that number is always going to be rational. It's always going to be some decimal value. All right, so now that we have that, let's sub and see if the base case works. So 1 minus a squared, is that going to be greater than 1 minus 2 times a? All right, well, let's just do this. So 1 minus a squared would be 1 squared minus 2a plus a squared. Is that greater than 1 minus 2a? Well, this front half matches that. So by adding a squared, yeah, it's always going to work. So the base case definitely does work. The next part of this is we have to, so this is assumption. We're going to assume that it works for n equals k. Okay, so if I did that, I would have 1 minus a to the k has to be greater than 1 minus k times a. So that's an assumption that we're going to use during our inductive step, which is what comes next. Green's my favorite color, so let's do our induction in green. So the inductive step, we are going to try to prove it when n is k plus 1. Okay? So when n is k plus 1, just writing this down, we would end up with 1 minus a times k plus 1 has to be greater than 1 minus k times a. Or sorry, k plus 1 times a. Almost messed that up just on my induction step. K plus 1 times a. All right, so let's work the left-hand side and see if we need to manipulate anything on the right-hand side to get us to our solution. So if I work this, we have to use our power rules, right? So plus 1 means that I've got 1 minus a times 1 minus a to the kth power. Okay, that is what that would do. I'm just going to go ahead because I feel like I might need to have this. So I'm just going to do 1 minus Ka minus, minus A there. It might be helpful. I don't know. I just want to have my options open so I can look for either one of those. Okay, so if that is what I have, I am looking for this right here, because that is the exact same as that. So that tells me that I can do 1 minus a times 1 minus ka, right? Because that's that over there. And I'm just going to go ahead and blow up those brackets to see if anything makes sense. If I blow up those brackets, I would end up with 1 squared plus ka squared. Sorry, I jumped a step there. 1 plus 1. So 1 times 1. 1 times 1. I am going to get this, don't you worry. So minus ka plus ka squared minus a. I did that backwards, but you got what I am doing. So this would turn into just gathering some like terms. I get 1 minus ka minus a plus ka squared. If I rewrite that, I could factor out an a there, and I get 1 minus a k minus 1. Actually, why don't I factor out I'll factor out a negative a. And if I do that, I get negative a coming out, and I get plus 1 plus ka squared. And I think we're actually in business, because if we look right here, what this would be is that would be greater than 1 minus, and it's written in a different order, but it still works out, k plus 1. This is the exact same as that. So if those two are the same, then when I add ka squared, I'm always going to get a value that is larger. So I would finish this by saying that because the base case, which is n equals 2, is true, and k plus 1, and when n equals k plus 1, assuming n equals k is true, works, then this is true for all n greater than or equal to 2, where n is an integer. Right, so I think that that solves that, and I think that that gets us to the end. I hope that was helpful. Good luck.